In the previous two videos, we have been analyzing the Leinard-Wickert potentials, and so I'm writing them here, where this is the electric potential V, here's the magnetic potential A, and I've written it in a little more compact form, where I've written in the denominator capital R, which you can see capital R is just this quantity right here. Okay, so what we did in the last, like I said, couple of videos was to find the gradient of V and then state the answer for the time derivative of A. And I've written them down here. So there was a lot of terms, there was a lot of algebra, and a lot of vector identities to take into account. But when you do, you get a form that looks a little bit like this, where I've kind of made this substitution where you get this variable omega. I'm calling it omega, it's not in the book, but both terms have that same omega right here. And then times that omega is a bunch of terms which have in it the distance r, the speed of light c, the velocity of the charge, and the acceleration of the charge, a. And so, you can take a look at this and see the form of it. Okay, so that's what we kind of worked out. Now, so we have these two quantities, we can then put them into the equation for the electric field. So the electric field is minus the gradient of the electric potential minus the time derivative of the magnetic potential, like so. And so we can actually clean this up a little bit by making a substitution and saying there's this new kind of velocity, u, which is the speed of light in the direction of r minus the speed of the charge. Okay, so when I do that, I can take a look at some of these terms, and if I take a look at, say, this term here in the denominator of what I've called omega, then what you can do is I could say take the quantity r dot u, and then r dot u would be that quantity right here. And so r with an arrow dotted into r with the hat just give me the magnitude of r. So I would have rc minus r dot v. Okay, so I could rewrite the denominator of the omega term. I could also rewrite some of what's in the gradient of v and the time derivative of a, because that would also fit, let's say, into these terms right here, and this one right here. Okay, so when I do that substitution, then I can clean this up and write this in a form which is a little bit more compact, and say the electric field is now Q over 4 pi epsilon naught. I now have a r dot u cubed in the denominator. I can factor out an r, and what I get in those brackets would be c squared minus v squared times u plus r crossed u crossed a, the acceleration. Okay, so that's by basically combining these two terms right here, the gradient of v and the time derivative of a, putting them in, doing the substitution for the velocity u, and then rearranging, basically doing a bunch of algebra, and you can end up with this result right here for the electric field. Okay, so we finally made it after 3 video lectures. We made it to an equation that has the electric field for the Leonard-Weichert potential. Okay, so for the magnetic field, so B is the curl of the potential A. And if I take a look at this, then what I would get is 1 over c squared, the curl of v times the velocity v. So I don't know if you noticed that, but if I go back up to when I started, then the v and a are essentially, what that leads to is a is just the potential v times the velocity. So that simplifies things a lot in trying to do this calculation. So now what I'm left with is the curl of v times the velocity, which I now have to write out the terms for the chain rule. So what I get is v times the curl of the velocity minus v crossed into the gradient of the potential. Okay, so this term here, the gradient, we've already worked that out. That's done. We can substitute that in. If I now look at the curl of the velocity, then I would have, if you remember from previous lectures, minus the acceleration crossed into the gradient of the time. And so in the end, what I get is the curl of A is minus 1 over c q over 4 pi epsilon naught 1 over r dot u. So now I'm staying with the u variable cubed r cross product with c squared minus v squared, the velocity v, plus r dot a times the velocity v plus r dot u times the velocity times the acceleration. Okay, so if you were to work that out, you would have these terms where now I've done the substitution for the gradient of the retarded time. I put that in. I took the cross product with the acceleration. So I'm skipping a bunch of the steps because it would take us an enormous amount of time to do that. Though I do recommend the students, if you have the time, go ahead and work that out. But in the end, what you would get is something that is a little more familiar, which is the distance cross product into all of these other terms. So if you notice that we could do some more algebra on this and try and clean it up, but what it turns out to be is that the magnetic field turns out to be 1 over the speed of light, r hat, crossed into the electric field, like so. And so what you find is that you have this connection between the magnetic field and the electric field, which we've seen before when we talked about electromagnetic waves, that the magnetic field is now the cross product of the electric field and the direction, let's say, of the charge. So what this tells us then is that the magnetic field is perpendicular to the electric field. The magnetic field is also perpendicular to the directionality, and what's even better is that if the velocity is 0, then the acceleration is going to be 0. So let's say we have a stationary charge, and if we have the stationary charge, that means that u becomes c times the direction, and then our electric field becomes q over 4 pi epsilon naught r over r dot c in the r direction cubed times c squared c r. So all the velocity and acceleration terms disappear, and we're left with this. And so we can go a little further and say q over 4 pi epsilon naught. And we have r dot r hat is just r. So that leaves us with c cubed r cubed c cubed r hat, and so the r cubed and the c cubes cancel. R cancels right here, that becomes r squared, and we're left with q over 4 pi epsilon naught of r hat over r squared, which is essentially Coulomb's law. So that's good. So we started with what looked like a very complicated potential equation that was both spatially and time dependent. And then we worked through and came up with a very general form of the equation written up here. But now if we take the special case of a stationary charge, and then what it leaves us with is Coulomb's law. So Coulomb's law then becomes an approximation or a special case to a much general explanation of electric and magnetic fields of moving charge. So in the end, what you get is, if I go back and show you this electric field equation, so then in the end what I have is basically this term here, which I've boxed in red, is the generalization of Coulomb's law. This term here, which I'm boxing in blue, is now a new term that has nothing to do with Coulomb's law. And instead, what it tells us is that first term is the generalized Coulomb's law, and the second term, which has the r crossed into u crossed into the acceleration, like so, that term is what's called the radiation field. And this dies off, so it falls off as 1 over r. And so we'll get to this in chapter 11, because what we're finding here is that if you have a moving charge, then that moving charge is going to radiate. It's going to radiate electric and magnetic fields, and those radiating fields are going to oscillate in the form of light. So right away we see if we have a moving charge that's accelerating, it is going to naturally radiate. So in the next lecture, we'll explore this a little bit and then go over an example.